Okay, let's go ahead and take attendance. Cassidy,
Here.
Alejandro, Liliana,
Here.
Lainey,
Here.
Cassandra,
Here.
Romeo Diaz,
Here.
Brenda,
Here.
Jasmine,
Here.
Josue,
Here.
Jade,
Here.
Valerie,
Here.
Edsel,
Here.
Paul,
Here.
Monique, Salvador,
Here.
Caitlin,
Here.
Kayla,
Here.
Romeo Ramos, Paula, Ricardo.
Here.
So Alejandro,
Here.
Alejandro is here. Paula, Paula is here, okay. What about Alejandro?
Here.
What about Alejandro? Alejandro or Romeo Ramos? Nope, okay. Okay, let's continue with chapter 10 today. Okay, so it says, suppose an event E occurs. Okay, the complement of event E, okay, is when E does not occur. Oh, Alejandro is here. Okay. Yeah, I got you, Paula. Thank you. Got you twice. The only one that's not here is Romeo Ramos. Okay, sounds good. Okay, so the complement of event E is the event E of event E is the event E does not occur. Okay, when this does not occur. So we use E bar, okay, to represent the complement. Okay. The probability of the complement PE bar, okay, is equal to 1 minus the probability of the event happening. Notice also that the probability of that happening is 1 minus the complement. Okay, so for example, if I said that 2/5, okay, of people, okay, I don't know, 2/5 of people like to brush their teeth, then what percentage or what fraction of people do not like to brush their teeth? Okay, what would be, yeah, it'd be 3/5, right? So it would be 1 minus the 2/5. So the probability of not brushing is going to be 1 minus 2/5 or 3/5. That's the complement. The not brushing is the complement of the brushing. Okay, you either brush or you don't. Okay, and that's the complement. Using Bucky's deck of cards. Okay, so where's Bucky's? Oh, where's Bucky's deck of cards? Let me share that. Okay, so here's Bucky's deck of cards, right? Okay, what do we want from Bucky? It says, what is the probability that Satchel, for Satchel not to draw a queen? We want him to not draw a queen. Okay, so the probability of not getting a queen would be 1 minus the probability of getting a queen. Right? So what's the probability of getting a queen? Well, let's look at our sample space here. How many queens are there? There's
4 out of 52.
Yep, there's 4 queens. So 4 out of 52. Very good. Okay, so 4 out of 52. Okay, so this is going to be 1 minus 1/13. And what's 1 minus 1/13? 12/13. The probability of not getting a queen is 12 out of 13. Okay, probability of 2 independent events. Suppose 2 events occur, event A and event B. If the probability of event B occurring is the same whether or not event A occurs, then the events A and B are said to be independent. Okay, so So they're independent if one of the probabilities does not affect the other. Okay, they're independent. Okay, when Satchel draws a card, he puts it back in the deck before drawing another card. What if Satchel draws a card, which is a spade, and does not replace the card back into the deck? Okay. Let's say Satchel then draws a heart. If Satchel had replaced the spade before drawing a heart, how would this probability be different from when he did not replace the spade? Okay, so what we're talking about here is when we do something called with replacement and without replacement. With replacement, we're replacing the card. Without replacement, we're not replacing the card. Okay, that's not replaced. Okay, so with replacement, meaning that I put the card back, what's the probability of drawing a spade, okay, and then a heart with replacement? If I replace the card, then it just goes back to the same sample space. If the probability of getting a spade, what's the probability of getting a spade? Let's look at our sample space. Probability of getting a spade, which is these like arrowhead looking things, okay, is 13 out of 52, or 1 out of 4. Okay, thank you, Romeo. Okay, so the ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king of spades. Okay, that's 13 cards out of 52. So I would have 13 out of 52 for the spades. But then what would happen if I wanted the hearts next? Okay, what would that give me if I wanted the hearts? Well, if I wanted the hearts and I put the card back, I would start with the exact same sample space. I would start with the exact same number of cards. I put the card back in the deck, I still have 52 cards. So now I want to know, well, what's the probability of getting a heart? Well, it's the exact same thing as the probability of getting a spade. It's still 13 out of 52. So this is going to be 13 out of 52, okay, which this is going to reduce to 1/4 times 1/4, okay, which is going to be equal to 1/16. Okay, that's with replacement. If it gets replaced, then we say that these are independent events. Okay, they're independent events. The getting a spade had no bearing on getting a heart. The probability of getting a spade and the probability of getting a heart were independent because I put the card back. I didn't change the dynamics of the deck. What about without replacement? What happens if I don't replace? Well, for my first card, it's still the same, 13 out of 52. But now what happens? How many hearts are there? Well, there's still 13 hearts, but how many total cards are in the deck if I don't replace it? Yeah.
39.
Yeah, thank you, Lainey. Thank you. I don't know who that was. That spoke. Oh, I'm not on full screen. There we go. Somebody. Okay, so maybe Romeo. I don't know. Okay, so yeah, 51 exactly. 51. Okay, now it's 51. Now these are not independent events. The probability of getting a heart, it depended on what happened with the spades. So without replacement, it's dependent, they're dependent events. They depend on each other now. So this is going to be 13 out of 52, that's 1 out of 4, times 13 out of 51 is going to be 13 out of 204. So completely different probabilities given the scenario. Okay. Suppose it will rain tomorrow in Houston, Texas, and it will also rain tomorrow in Galveston, Texas, a city near Houston. Are these two events independent? Probability of rain in Houston and the probability of rain in Galveston. And what I like to do is draw something called a Venn diagram here and just say, hey, you know what? We've got Houston and Galveston. One may rain and one may not rain. They may both rain, right? We could get some overlap here. They may both rain. And if it rains tomorrow in the same area, well, they're probably what? They're probably not independent. They're probably dependent events. Okay, because you're in the same general area. Okay, since they're in the same weather system. Okay, so in the same weather system, it's generally, they're going to be dependent, not independent events. Okay, working with events. Okay, if they are independent and we have both occurring at the same time, then we just multiply the probabilities together. The probability of A and B occurring is equal to the probability of A times the probability. And we already saw that in this example that we just did. What's the probability of getting a heart and getting a queen if I replace the cards? Then that's the same as the probability of getting a heart times the probability of getting a queen. If I replace it, then it's independent. Okay, then this formula here works. So what's the probability of getting a heart? 1 out of 4. What's the probability of being a queen? 1 out of 4. Oh, that's right. Sorry, this should be spade. Sorry. 1 out of 4. Okay, and so that's just 1 out of 16, which we saw before. Okay. Pretty easy. Okay, in the drawer, there are 10 pairs of socks, 6 which are white. Okay, so 10 pairs of socks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pairs of socks. 6 are white, and then there's 4 others. I don't know, maybe O for other, and then white, 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 white. Is that it? Is that my 10? I think so. Okay. And 7 shirts, 3 of which are white. Okay, so 7 shirts. 1, 2, 3, 4, 5, 6, 7. So this is my socks. This is my shirts. Okay, 3 of which are white. Okay, white, 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 and other. Oops, not 0. Other. Okay. So what is the probability of randomly selecting a white pair of socks? What's the probability of getting a white pair of socks? Wasn't that just 6 out of 10? Probability of getting a white pair of socks. Okay, and, oh, it says and here, and a white shirt. White socks. Okay, and white shirt. Well, since the socks and the shirts don't affect each other, those probabilities don't influence, the socks don't influence the shirts and the shirts don't influence the socks. Okay, then these are independent probabilities, and so I can say, what's the probability of getting white socks times the probability of getting a white shirt. And so this is going to be 6 out of 10, right, times 3 out of 7. Okay, 6 out of 10 times 3 out of 7. I'm going to reduce this 6/10 to 3/5, and that's going to give me 9/35. Wait, what about the or statement here? Okay, or I want A or B. Now, and, okay, is kind of an inclusive. Think of the and statement as both, and think of the or statement as either. Okay, and is both, and or is either. Either occurs. So I'm going to use, again, the Venn diagram here to kind of see what's happening here. If this is the probability of A, and this is the probability of B occurring, right? Well, think of it this way: if this is like blue eyes, and this is like brown eyes, then the probability of A occurring or B occurring, that's, I'm just going to add them together because they're independent. You either have blue eyes or you have brown eyes, right? So if it's independent, then there's no overlap. For independent events. However, what if the a event can take on two or more different characteristics at the same time? Well, then we would have something called overlap. We would say, well, let's say that somebody has brown eyes and blue hair. Could someone have brown eyes and blue hair? Well, yeah, sure. You can dye your hair whatever color you want. So could there be overlap here? Yeah. So what I don't want to do is I don't want to count that overlap twice. I'm either going to count it with A or I'm going to count it with B. I don't want to count it twice, so I have to subtract one of those overlaps off. Okay, again, think of these like two circles, and then if I do the probability of A here, then one of those overlaps is going to get counted already, and so I do not want to count this piece twice. Okay, in my probability, I don't want to count the overlap in A and B. So the way that I count it only once is I subtract it off. I subtract off the overlap, and that's exactly what we're doing here. Okay, if there's no overlap, then we just add the probabilities together. Then it's just probability of A plus probability of B. But if there is overlap, then we have to subtract off one of the overlaps. Okay. Okay. Let's do an example of this, and hopefully it'll make more sense. Okay, recall from example 1.3, Bucky has a deck of 52 cards, standard cards, with his friend Satchel to draw a card. After Satchel draws a card, he puts it back in the deck. Okay, so these are going to be independent probabilities. Fine. Okay, that's good. Okay, so find the probability of Satchel drawing a queen. Okay, so what's the probability of him getting a queen? Well, there are 4 queens out of 52 cards. So that's 1 out of 13. Okay. What's the probability of Satchel drawing a spade? Okay, probability of Satchel drawing a spade, that is going to be, okay, how many spades? 13 spades out of 52, and that's going to be 1 out of 4. Okay, nice, nice, nice. Okay, find the probability of Satchel drawing a spade or a heart. Okay, so probability of a spade or a heart is going to be equal to what? It's going to be equal to the probability of a spade plus the probability of a heart minus the probability of getting a spade and a heart. Well, can you draw a spade and a heart at the same time? Is there any card that has both a spade and a heart on it? No. No. You cannot draw a spade and a heart with one draw. So those are mutually exclusive events. They're independent. And so there is no overlap. You can't have spade and heart at the same time. It's just not going to happen. Okay, they're two different suits. It's like having brown eyes and blue eyes at the same time. You either have one or the other. Okay, or you call it something else. Okay. So we know that there is no overlap here. The overlap here is 0. Probability of getting a spade and a heart at the same time. Okay. Okay, then it's 0. Probability 0. Okay, probability spade is what? Probability spade is 1 over 13. Probability of heart is 1 out of 4. I might just go back to the 52s to make it a little easier. Probability of spade is 1. No, I'm just going to do 1 out of 4. What's the probability of getting a heart? It's 1 out of 4. So this is going to be 2 out of 4 or 1/2. Okay, now this was when it was independent. Remember, those were two circles that had no overlap. Probability of spade and probability of heart, we just add them together. What about the probability for Satchel drawing a queen or a spade? A queen or a spade? Well, the probability of getting a queen or a spade is equal to the probability of getting a queen plus the probability of getting a spade minus the probability of getting both a queen and a spade. Why? Because we want to get rid of that overlap. Is it possible to get the queen of spades? Yes. How many cards are the queen of spades? 1 out of 52. There's a 1 out of 52 chance that I would get the queen of spades. Right? So I want to subtract off that probability because I don't want to count it twice. I don't want to count this one card in the queens and in the spades at the same time. The probability of getting a queen, that's 4 out of 52. The probability of getting a spade, that's 13 out of 52. And so now I have to subtract off that 1 out of 52. So this is going to be 12 plus 4 is 16 out of 52. And if I divide both top and bottom by 4, I get 4 out of 13. And that's the probability of getting a queen or a spade. And let's see if that makes sense. They're saying that there's 16 cards here that match that criteria. Let's go back to our deck, our standard card deck here, and see what criteria do we want these to meet. We either want a queen. Okay, so where's the queens? They're right here. Okay, or I want a spade. Oh, okay, that's this here. Okay, so how many total cards do I have? Well, let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yeah, 16. Now, which card did I not want to count twice? Right there, right? We didn't want to count that one twice. So we found if we added up the number of queens, we'd get 4. If we added up the number of spades, we get 13. And we'd have to subtract off the 1 that was the overlap. And that's exactly what we're doing with the probability. Okay. Okay, probability of at least 1. Of at least 1. Let's know what at least means. Okay. My business calculus students, I think I asked this on an exam or something, and they're like, what does at least 1 mean? And I'm like, at least 1 means 1 or more. So make sure that you know that, right? So if you have a sample space of 1, 2, 3, 4, 5, and 6, then what does at least 1 mean? It means 1 or more. It's 6 out of 6. Right? It doesn't mean less than 1, which would be 0 out of 6. Does that make sense? Make sure you understand what more, at least means and at most means. At most, that's your lower bound. At least, sorry, at most is your upper bound. At least is your lower bound. Okay, so think of this as at least. Think of this as at most. Okay, make sense? Okay, and you can always put it in terms of dollars too if it becomes, you just say, hey, I make at most $90 a day. What does that mean? That means that your employer is not going to pay you more than $90 at most. If you said I make at least $100 a day, then you're making $100 or more. That's your floor, we call it. Your floor is $100 per day. Whereas your ceiling for at most is $90 a day. That's your ceiling and your floor. Right? Okay, I know the English is kind of confusing, especially if English is not your first language. Okay, there are probability problems which are stated. What is the probability of at least? We could add the probabilities using the probability rule above, but this can be very long and tedious. For example, let the sample space be 1 to 100. What is the probability of what is the probability of a number that is at least 5 occurring? What does that mean? It means we want 5 or more. 5 or more. Okay, that's what at least means. Okay, or more. At least. Okay. Okay, we could see that this could take a while. You'd have to find the probabilities for 5 through 100. Or we can use the converse, right? The complement, right? What's the probability of at least 1? Well, the probability of at least 1 is 1 minus the probability of none. Okay, so the probability of at least 1 is 1 minus the probability of none. Okay, what's the probability of at least 5? Well, the probability of at least 5 is 1 minus the probability of less than 5. Okay. Probability of at least 5. So all you have to do is find what the probability of 1, 2, 3, 4, 5, or sorry, 1, 2, 3, 4. Okay. And then subtract that from 1 and you would get your probability. It says now use the formula to obtain the probability of a number that is at least 5 occurring in the set above. Okay, well, we just did that. The probability of at least 5 is equal to 1 minus the probability of less than 5. Okay, that's the complement. And so the probability of at least 5 is equal to 1 minus the probability of 1 occurring, probability of 2 occurring, probability of 3 occurring, probability of 4 occurring. Do I put 5? Do I include the probability of 5? Nobody wants to answer. That's okay.
I have a question quickly. Sorry. Inside of the parentheses in the first one, like P parentheses less, what's that one next to the 5, like that middle word? I can't say it if it's a word or a number.
Than.
Oh, then. Okay. That's all. It's because I'm just trying to catch up. I'm a little stuck on this, but I'm just trying to catch up. Thank you.
Okay, so should we include 5? That's the question on the table. Should we include 5 in less than 5? Why do you say?
For at least 5 or less than 5?
I said less than 5. At least for at least 5 is 5 included. Yeah, 5
Yeah.
is
No, you wouldn't want 5 because you want whatever's less than it.
less than 5. So
Yeah.
that is not included. Okay, So the 5 goes with the at least. It does not go with the less than, right? So think of it as 1, 2, 3, 4, 5, 6, 7, dot, 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 forever, right? Okay, what is at least 5? Well, that's 5 or more. And what would be less than 5? It would be 1 through 4. Hey, that rhymed. I'm a poet. I didn't know it. We really need to stop this rhyming. I mean it. Anybody want a peanut? That's from the Princess Bride. Okay, now let's move on. Okay, so at least 5 is equal to 1 minus the probability of 1, probability of 2, probability of 3, and the probability of 4. Okay, so that's what they wanted there. Okay. Okay, next one. In the drawer, oh great, there are 10 pairs of socks, 6 which are white, 7 shirts, 3 of which are white. If a pair of socks and a t-shirt are selected at random, what's the probability that at least one of the garments is white? Okay, so the probability at least one garment is white. Okay, so that might be pretty hard to figure out. Okay, probability that at least one is white. So we could get, I mean, there'd be a lot of possibilities here. We could get a white with, we could get up to 6 white socks and up to 3 white shirts, and any combination of those. That's a lot of different combinations to run. Okay, where I just get at least one. Well, what's the opposite of this? It would be 1 minus the probability that we get none white. Right? None white. Now that's a little bit easier to calculate. What's the probability that we get no white socks? Well, that's just 4 out of 10. What's the probability of getting no white shirts? Well, that's just 4 out of 7. So I'm going to reduce this to 2/5, and that's going to become 1 minus 8/35, which is going to become 35 over 35 minus 8 over 35, which is equal to 27 over 35. So you have a 27 over 35th chance of selecting, okay, at least one white sock or one white shirt, okay, by randomly choosing from your sock and shirt drawer. Okay. Okay, given a table below for a group of adults at which is divided into gender and the hand that they write. Okay, so we got males and females and right hands and left hands. Okay, find the probability of a randomly selected individual to be male and left-handed. What's the probability of being male and left-handed? Well, how many? So probability of being male and left-handed. Okay, so that's going to be the overlap here between male and left-handed. So that's going to be 12 out of a total, how many people? Yeah, 100.
Oh, wait.
100, right? Find the probability that a individual, selected individual, well, how many individuals are there? There are 100.
100.
Yeah, exactly. Okay, there are 100 individuals, so I'm going to reduce this by 4. This is going to become 3/25. Okay, always reduce your fractions. Okay, B, find the probability of a randomly selected individual to be male or left-handed. Okay, so probability of male or left-handed, that's going to be the probability of being male, plus the probability of being left-handed, minus the overlap of probability of male and left-handed. Oh, okay. Okay, so what's the probability of being male? Well, how many males out of how many individuals? Well, there's 50 out of 100. So that's 50 out of 100. What's the probability of being left-handed? Well, it looks like there's 20 out of 100 total people that are left-handed. So this is 20 out of 100, right? Minus the overlap. Well, what's the overlap? That's 12 over 100, right? Minus the overlap. Why? Because I would have counted it twice. Okay, I want all the left-handers and I want all the males, right? And I just don't want to count the male and the left-handers twice. Okay, so the males are 50 out of 100. The left-handers are 20 out of 100, but I don't want to count the male left-handers twice in my group, so I have to subtract off once. Okay. Okay, so this is going to be 50 plus 20, which is 70, minus 12, which is 58. So this is 58 over 100. Those are both divisible by 2. So I get 29 over 50. Okay. Find the probability of a randomly selected individual to be a woman given she is right-handed. Now this given is very interesting, okay? Because what this is saying is it's saying what's the probability of that a randomly selected individual to be a woman, so woman, given that she is already right-handed. So this line here means given. Okay, this is the probability that it's a woman given is right-handed. And what we do when we see that given, we say, hey, that's the sample space we are given, which means that this person has to be right-handed. If it's given that she's right-handed, if it's given that that person is already right-handed, then we only look at the right-handers. Only look at those with the given trait. We're only looking at the right-handers. We're only looking at these people. Okay, those people are the only ones that count. So let's go back to our table and see who are the right-handers. Who are the right-handers? Well, there's 80 of them. Boom, right-handers. And how many of them are female? 42. So the probability that someone is a woman, okay, given that they're right-hander, is going to be equal to, okay, the number of women that are right-handed. Well, how many is that? The number of women that are right-handed is 42. Okay, 42. And over the total number of right-handers. Well, that's 80. This is divisible by 2, which becomes 21 over 40. And that's the probability. Okay, this thing with the given, it has a name. It's called conditional probability. It's based on a condition. Okay, it's called conditional probability because it's probability with a condition. It's a set condition. Okay, if I said, you know, what's the probability of, people being Republican given that they wear brown shoes? Well, what population am I just looking at? I'm just looking at the people who wear brown shoes. Everyone who doesn't wear brown shoes, I could care less about. Does that make sense? Whenever you have a given, it's basically, oh, those are the only people I'm looking at. Okay, so conditional probability. Suppose two events occurred, events A and B. The probability event B occurring, given that event A already occurred, is represented as the probability of A and B is equal to probability of A times the probability of B given A. Okay. So this is a little formula that we can have for AB. It usually is written like this, which I don't know why they wrote it like they did here. It's usually written like this. The probability of B given A is equal to the probability of A and B occurring over the probability of A occurring. Okay, so that's generally how it's written, although it's kind of hiding. There, that's better. This is generally how you'll see it in textbooks. I don't know why the author wrote it the way she did here, but whatever. Okay, we take the probability of the overlap of A and B divided by the probability that A occurred, and we get the probability of the given. Okay. Okay, consider Bucky's deck of cards and his friend Satchel. Okay, well, we're going to go back to Bucky's deck of cards, Bucky's famous deck of cards here. Okay, so what's up with Bucky's famous deck of cards? I don't know, but let me try to erase this. Okay, so Mr. Bucky makes me think of like Bucky Barnes from Marvel. Bucky, who names their kid Bucky? That's just child abuse. Come on. Okay, there you go. I'm just stalling for time if you didn't realize. There, wait, go, there. Okay, I'm ready. Okay, consider Bucky's deck of cards and his friend Satchel. What is the probability of Satchel drawing a heart without replacing the card and a spade? Okay, so we want a heart and a spade. Probability of a heart and a spade. Probability of a heart and a spade. Okay, so at the same time, right? Okay, so he doesn't replace the card though. He doesn't replace the card. Okay, so what's the probability of a heart and a spade? Well, what's the probability of getting the heart? Probability of getting the heart is 13 out of 52 times, what's the probability of getting the spade now? The probability of getting the spade, okay, is the probability of the spade given that I already took out the heart. I've already taken out the heart. So this is going to be 13 out of 51. We already did this problem earlier. Okay, I believe. Maybe not. Maybe it's a different scenario. So let's see what happens here when we reduce this. This is going to be 1/4 times, okay, times 13/51. Okay. Is it 13/51 or is it heart and then a spade? Yeah, should be 13/51. Let me see. My answer is not coming out the same. 1 second. Their answer. Why is that? Question number 14, right? Nope. Yeah, because I was wrong. Oh, no. Yeah, that's good. Yeah, that works. Okay, so it should be 13 out of 204. Yes, correct. Okay, so this is the same thing that we did before, 13 out of 204. Perfect. Okay. Okay. What about consider Bucky's deck of cards and his friend Satchel. What's the probability of Satchel drawing 2 clubs without replacing him? So we're going to draw a club and then a club. Okay, what's the probability of getting a club and then another club? Well, probability of getting a club is 1 out of 4 or 13 out of 52. What's the probability of drawing another club but without replacing it? It's 12 out of 52. Or sorry, 12 out of 51. Why? Because both of them went down, right? We look at our sample space and we look at our clubs here. Say that I chose the ace of clubs, but I didn't put it back. Well, that means that instead of 13 out of 52, I now have 1 less in each category. I have 12 clubs out of 51 total cards. Okay. 12 clubs out of 51 total cards. So I'm going to cross cancel here. These are both divided by 4. So this is 3 over 13. Ooh, look at that. 13 over 13, that's 1 over 1. Okay, and 3 over 51, 3 goes into 51 17 times. I'm just going to write this like this. And then if I reduce this, this is 1/17, so 1 over 17. Okay, so a lot of reducing of the fractions there. Okay, okay, and then last example. Students always get excited when I say that. I don't know why they do, but they always get excited when I say last example.
Wait, can you go back up real quick?
Yeah.
Professor? Thank you.
Is that good? Okay. Okay, suppose G-Pod manufactures 100 of the new phones, the G phone. Okay. Because the G phone is new to the cell market, there's an estimated 15 G phones that are defective for 100 manufactured. Okay. The creator of the G phone decides to test 3 out of the 100 phones. What's the probability that at least 1 G phone is defective? So the probability that we're out of the 100 manufactured is defective. Probability that at least 1 is defective is equal to 1 minus the probability that none are defective. Okay, none are defective. Well, what's the probability that 1 is defective? Well, that would be 1 minus the probability. So what's the well, let's say what's probability of 1 being defective? Isn't it 15 out of 100? Right. So for every 15 out of 100, 1 is defective. Or sorry, every 15 out of 100, 15 are defective for every 100. Okay, so I could reduce this. I could divide both top and bottom by 5. And this would be 3 over 20. So the probability that one of them is defective is 3 out of 20. Okay. What's the probability of it not being defective? What's the probability of not defective? Okay. What's the probability of this not being defective? Yeah, thank you, Lainey. It's 17 over 20. It's 1 minus 3 over 20, which is 17 over 20. Exactly. Okay. And so if that's the probability of 1 not being defective, what's the probability that none of the 3 are defective? Well, what I'd have to do is I'd have to say the probability of none of 3 defective is equal to 17 over 20 times 17 over 20 times 17 over 20. Okay, and that's going to be some sort of huge number. Okay, I could probably turn this into a decimal at this point, but 17 over 20 is 0.85. So this is 0.85. It's 0.85 times 0.85. It's 0.85. Okay. And so that's 0.85 times 0.885. 85 times 0.85 is 0.614125. Okay, so that's a problem that none are defective. Well, what's the problem that at least one is defective is 1 minus this number. I'm going to take the calculator and go 1 minus 0.614125. Okay, because the opposite of none is at least 1, right? The opposite of none defective is at least 1 is defective, right? Out of 3 phones, we want at least 1, so that's 1 minus none. So this is going to be 1 minus, okay, probability of at least 1 is 1 minus the probability of none. So this is going to be equal to 1 minus 0.614125, which is 0.38575. And I could round to 3 decimals if I really wanted to, 0.386. Okay, or I can make it a percentage. So 38.6% of the time, I will get at least 1 defective phone when I buy 3. Okay, so 38.6% of the time, I will get at least 1 defective phone when I buy 3. When I test, I'll say test 3, because that's really what's happening here. They're testing these for defectiveness. Okay. There. Okay, that's all I got for you for today. So I'll see you guys on Monday. Okay, make sure that you do your worksheet in conjunction with your homework. Okay, we're on module 11 this week. Okay, is there a worksheet? Maybe there's not one. I'll have to check. So, okay, see you guys later. Oh, sounds good. Thank you, Joel. And yeah, and Romeo was also here, so I gotta make sure that I count him as here as well. So yeah, I got you. I got you, Joel. Thanks. Everybody was here. That's amazing. That's amazing. It's crazy. Sounds good. You too.